Going to extend our discussion of limits, and I do have up here what we talked about yesterday. We spent a lot of time talking about function values, and we even looked at a particular function, and we said as we got really close to 2, the function approached the value of 1.33. All right? And when we said function value, remember when we think function value, we're thinking y values. All right? So we are comparing as we approach a certain value on the x, okay? Let me get a different color here. As we approach a certain value on the x-axis, we are interested in what is the function approaching in terms of its actual function value. And that's what we talked about yesterday. And we said if we can approach a specific value, then we say that the limit, LIM is short for limit, of a function as we approach a certain value is L. Now, let's consider a very basic problem, something like this. How about the function 3x plus 6? Okay? Very, very basic function. What if I wanted to find the limit as x approaches 7 of 3x plus 6? This would be an example problem. We'll call this number 1. If I wanted to find the limit of 3x plus 6 as x approaches 7. Now we talked yesterday about verbally nagging. We're not going to do that on every problem, but let's do it a little bit here. If I were to graph this, 1, 2, 3, 4, 5, 6, this is just a linear that goes through 6 and has a slope of 3. And I'm not going to get real technical here. Something like that. All right? There's my linear. We are wanting to know the limit of this function as x approaches 7. So down here is 7. 1, 2, 3, 4, 5, 6, 7. If I wanted to know the limit of this function as x approaches 7, what would I do? Somebody said it. 3 times 7 plus 6. 21 plus 6 is 27. Isn't that the function value? Right? If I were to come to 7, remember, my function is 3x plus 6. If I do f of 7 and do 3 times 7 plus 6 and get 27, okay, that is the y value up here, isn't it? Isn't that the y value it is approaching? As we get really close, remember what we said yesterday, we're going to get really close to 7. If I look at it from both directions, both from the left and the right, the function is approaching 27. Does everybody agree with that? Yes. Okay? So it's a very simple concept if we have a very basic equation. This linear, does it have anything that's undefined or any issues like that? No, it doesn't. So it's pretty easy if you have functions that their domain is all real numbers. Let's look at another example. How about the limit as x approaches negative 3 of x squared plus 1? Yeah, the answer to that last problem was positive 27. How about this one? What kind of function do we have? Don't we just have a quadratic that's been moved up 1? There's nothing undefined. So if I'm wanting to know what function value this is approaching, then all I have to do is substitute, right? All I need to do is plug in negative 3. Negative 3 squared plus 1, that's going to be 9 plus 1, which is 10. So the answer to this problem is 10. Now let's think about that graphically. Here's x squared plus 1, right? Over here is negative 3. If I were to plug negative 3 into the function, I get 10. All right? So that's considering it graphically. You don't have to. The analytic method is totally sufficient for that problem. You could also look it up on your table of your graphing calculator, like we did yesterday, and look at it numerically. But there's really no need to on an easy problem like this. Okay? Now, what I'd like to do now is consider a couple of different situations that maybe are a little bit, maybe not trickier, but let's consider this function. Now, if I am considering this function, all right, if we were to plug this into the graphing calculator, all right, and let's just do that real quick. X squared plus x minus 2 is the numerator, divided by x minus 1 as the denominator. And we'll just go zoom standard. Well, that's funny. It just looks like a linear to me. That's interesting. As a matter of fact, it looks like a linear that goes through 2. Well, my cursor isn't working to take a screenshot, so I will do it this way. It looks like a linear. Okay. There, I solved my little mistake. That looks like a linear that is going through 2, doesn't it? Now, that function doesn't look like a linear. As a matter of fact, do you see something that is undefined? 1. So what if I wanted to do the limit of this function as x approaches 1? How could I find that limit? Well, there's a couple things to consider. Don't we have a graph here that is giving me some information? Okay? As I approach 1, which is right here, it looks like there's a function value that this is approaching. So how could I figure that out? Well, maybe I could look at it numerically. Maybe I could go to the table. I'll go to my table setup. We're wanting to get close to 1, so maybe I will start at 0.9 and go up by 0.01 and go to my table. And it looks like to me there's an error at 1, of course, but what does it appear that it is approaching? It looks to me like it's approaching 3. Okay? So if I look at this numerically, it looks like it's approaching 3. Okay? Looks like it's 3. That's looking at it from the table. And the graph shows me the same thing. My graph isn't really zoomed in enough, but I think we could see the same thing on the graph. How about analytically? Well, if I wanted to look at this analytically, I could factor it. watch what happens. If I factor the top into x plus 2 times x minus 1, I can get out the slasher. And I'm left with a function that looks like x plus 2. Isn't that what this looks like? Doesn't it look like x plus 2? We just happen to have a hole at 1. Okay, so there's actually a hole here. So now what? We can do this analytically. I can find the limit as x approaches 1 of x plus 2 analytically. Don't I just plug in the 1? 1 plus 2 is 3. And that's the same thing we saw from the table. Okay? Now what if I wanted to find the limit as x approaches 7? Do I need to even go through all of this? I wouldn't. I would get the same thing, but isn't it easier to work with x plus 2 than it is to work with this big mess up here? Much easier. It's going to be, I'm going to work with x plus 2, so it's going to be 7 plus 2, which is 9, all right? But I don't have to worry about that 1, okay? What I'm getting at is I could have worked with the original function the way it is, and I still would have got 9. Okay? Let's just verify that. 49 plus 7 minus 2. 56 minus 2 is 54. Okay? 54 divided by 7 minus 1, which is 6. Isn't that 9? Okay, so you could have used the original function because now we're not at a place where the function is undefined. Okay, so if you get away from where it's undefined, you can just plug it in and go. All right, plug it in numerically. Let's look at another one. How about this function? The limit as x approaches 2 of 2x squared minus 5x plus 2 all over 5x squared minus 7x minus 6. And we're doing the limit as x approaches 2. Well, here's how I would approach these problems. It's not going to hurt to do substitution. Okay? Right? If you do substitution, then what happens? So let's just go ahead and plug in 2 and see what happens. 2 times 2 squared minus 5 times 2 plus 2, that's the numerator, over 5 times 2 squared minus 7 times 2 minus 6. Well, on top I'm going to have 2 times 4, which is 8. 8 minus 10, which is negative 2. Negative 2 plus 2 is 0, but what happens in the bottom? I'm going to have 5 times 4, which is 20. 20 minus 14 minus 6 is a 0 in the denominator, which is a problem. Yeah. So guess what? Substitution at the beginning won't work here. All right? So we tried to substitute first. And we got a frowny face. So now let's try to factor. Okay? So this was step 1. Step 2, let's now try to factor. And I'm going to save you some time and just tell you how it factors out. It factors out into x minus 2 times 2x minus 1 all over x minus 2 times 5x plus 3. How convenient that when we get out the slasher, the x minus 2's go away. the thing that caused us to have a 0 in the denominator goes away. So now I just have this. Now I just have 2x minus 1 over 5x plus 3. And remember, I'm doing the limit of that as x approaches 2. All right? If you didn't get the last screen, here it is. So now I can try substitution. Let's try it now. Let's try substitution now. 2 times 2 minus 1 over 5 times 2 plus 3. 4 minus 1 is 3. 10 plus 3 is 13. Good news, we do not have a 0 in the denominator. How could I, that is doing it analytically. How could I verify that? I could look at the graph. I could look at the table. Okay? Unless you're asked to. Okay? Now, how about this problem? I'm trying to give you some techniques here that will help you in homework. How about the limit as x approaches 9 of x minus 9 over the square root of x minus 3?
So is it basically like just finding f of whatever the approaching?
Well, we have to, like I'm showing you, sometimes you have to manipulate the function before we can find the limit. If I try to plug in 9, remember we try to substitute first.
It won't work.
Substitute, I think all of you can see that that's a problem. But there's nothing I can do to factor this one, is there? So this goes back to a little skill we learned in pre-calculus, which is multiplying by the conjugate. If I multiply the top and bottom by the square root of x plus 3, okay, this is a little pre-calculus skill, then the denominator is a difference of two squares, and it becomes x minus what? 9, doesn't it? What's on top? X minus 9 times the square root of x plus 3. Can I get out the slasher? I can. And now I can take the limit as x approaches 9 of the square root of x plus 3. Now I can just substitute. The square root of 9 is 3. 3 plus 3 is 6. A lot of this is just learning about function values. All right? How about the limit as x approaches 0 of 1 over x? I'm going to do this one in two parts. I'm going to do this one, and then I'm going to do this one. Same function, but we're looking at two different values. This is why we have to know our functions. If I just try to plug in 0, I get 1 over 0, but wait, what does this function look like? Do you remember? It's the reciprocal function. Doesn't it look like this? This is our first situation where the limit does not exist. Okay? The limit in this case does not exist. Or you could just write DNE. The reason it does not exist is because of our definition that we did a few pages back. I'm scrolling back here. Be patient with me. As x gets close to a, does that function value get close to some real number, L? Well, if you look at the reciprocal function, it's not even close. As I look at it from the right, As I come in this way, it's going way up to positive infinity. As I come at it this way, it's going down to negative infinity. It is not approaching a single value L. So it does not exist. Let's look at part B though. If I am doing the limit as x approaches 2 of 1 over x, does it approach a single value L?
Yeah.
It does. This one is just 1/2. You just put the 2 in. So it all depends upon what x value you are approaching and what the function is doing there. All right, that's very important to consider. Now, one last special function that shows up over and over again in AP Calculus. Sin x over x. This one shows up in AP Calculus all the time. Shows up on the AP exam frequently. This is one that you have to know something about. I'm going to give you the answer ahead of time, and then we're going to look at why. This is 1. Okay? And the situation that's going on here, if we look at this graphically, which we're running a little short on time, so I'm just going to sketch this for you. This thing oscillates around the x-axis like that. But there happens to be a hole right here at 0. Okay? And this value, right here, this y value is 1. So the limit of this thing, as x approaches 0, is 1. It is very difficult to show this analytically. We may do it later. It's very hard to show it analytically. So in this case, we want to consider the graph. And if you looked at it on the table, you would see the same thing. Okay? And we are going to stop there for today. We are going to spend more time on this function later, but we're going to stop there for right now.